Let me show you how to be a good busy and change your predictions.
In this episode, Dmitry Bagaev discusses his work in Bayesian statistics and the development of RxInfer.jl, a reactive message passing toolbox for Bayesian inference. Dmitry explains the concept of reactive message passing and its applications in real-time signal processing and autonomous systems. He discusses the challenges and benefits of using RxInfer.jl, including its scalability and efficiency in large probabilistic models. Dmitry also shares insight into the trade-offs involved in Bayesian inference architecture and the role of variational inference in RxInfer.jl. Additionally, he discusses his startup, Lazy Dynamics, and its goal of commercializing research in Bayesian inference. Finally, we also discuss the user-friendliness and trade-offs of different inference methods, the future developments of RxInfer, and the future of automated Bayesian inference. Coming from a very small town in Russia called Nizhnekamsk, Dmitry currently lives in the Netherlands, where he did his PhD. Before that, he graduated from the Computational Science and Modeling Department of Moscow State University. Beyond that, Dmitry is also a drummer. You'll see his core drums if you're watching on YouTube, and an adept of extreme sports like skydiving, wakeboarding, and skiing. This is Learning Bayesian Statistics, episode 100, recorded January 25, 2024.
Let me show you how to be a good busy and change your predictions.
Dmitry Bagaev, welcome to Learning Bayesian Statistics.
Thanks for inviting me for your great podcast. Really, I feel very honored.
Yeah, thanks a lot. The honor is mine. That's really great to have you on the show. I have so many questions for you, and yeah, like we're also gonna be able to talk again about Julia. So that's super cool. And I want to thank, of course, Albert Podusenko for putting us in contact. Thanks a lot, Albert. It was a great idea. I hope you will love the episode. Well, I'm sure you're going to love Dmitry's part. Mine is always more in the air, right? Well, Dmitry, thanks again, because I know you're a bit sick, so I appreciate it even more. And so let's start by basically defining what you're doing nowadays, and also how did you end up doing what you're doing, basically?
Yes, so I'm currently working Eindhoven University of Technology in Bayes Lab, and I just recently finished my PhD in Bayesian statistics, essentially. So now I'm just like supervise students, lead some of the projects there. And Bayes Lab itself is a group in the university that primarily work on like a real-time Bayesian signal processing, and we do research in that field. And the slogan, let's say, of the lab is sort of like is natural artificial intelligence, and it's phrased like specifically like that because there cannot be natural artificial intelligence. So it's like a play of words, let's say. And the lab is basically trying to like develop automated control systems or like novel signal processing applications, and it's basically inspired by neuroscience. And we also opened a startup with my colleagues, which is called Lazy Dynamics, and the idea is basically to commercialize the research in the lab, but also to find the new funding for new PhD students for the university. But it's still quite young, so we are still like less than 1 year, and we are currently like in search of clients and potential investors. But yeah, my main focus still remains being a postdoc in the university.
Yeah, damn, fascinating. So many things already. But maybe what do you do in your postdoc?
So my main focus, like primary, is supporting the toolbox that we wrote in our lab. That I am a primary author. We call this toolbox RxInfer, and this is a like essential part of my PhD project. And basically, I love to code, so more or less like my scientific career was always aligned with software development. And the RxInfer project was a really big project, and many other projects in Bayes Lab, they depend on it. and it requires maintenance, like bug fixing, adding new features, performance improvements, and we are currently have several sub projects that we develop alongside for the RxInfer. That's just like the main focus for me. And as something else, I also supervise students for these projects.
Yeah, of course. That must also take quite some time, right?
Yes, exactly.
Yeah. Yeah, super cool. So let me start basically by diving a bit more into the concepts you've just named, because you've already talked about a lot of the things you work on, which is a lot, as I guess listeners can hear. So first, let's try and explain the concept of reactive message passing in the context of Bayesian inference for our listeners who may not be familiar with it, because I believe it's the first time we really talk about that on the show. So yeah, talk to us about that. Also because from what I understand, it's really the main focus of your work, be it through RxInfer.jl or Lazy Dynamics or Bayesian. So let's start by having the landscape here about reactive message passing.
Yes, good. So yeah, RxInfer is what we call reactive message passing based Bayesian inference toolbox. And basically, in the context of Bayesian inference, we usually work with probabilistic models. And a probabilistic model is usually a function of some variables, and some variables are being observed, and we want to infer some probability distribution over unobserved variables. And what is interesting about that is that if we have a probabilistic model, we can actually represent it as a graph. And for example, if we can factorize our probabilistic model into a set of factors, the graph would be such that each node will be a factor and each edge will be a variable of the model, more like hidden states, and some of them are observed or not. And basically, message passing by itself is a very interesting idea of solving Bayes' rule for a probabilistic model defined in terms of the graph. So it does it by sending messages between nodes in the graph along edges. And it's quite a very big topic, actually. But essentially, here to understand is that we can do that, right? So we can reframe the Bayes rule as something that passes messages in the graph. Reactive message passing is a particular implementation of this idea. So because in the traditional message passing, we usually have to define an order of messages, like in what order do we compute them. Because it may be very crucial, for example, if the graph structure has loops. So there's like some structural dependencies in the graph. And reactive message passing basically says, okay, no, we will not do that. We will not specify any order. Instead, we will react on data. So, and the order of message computations becomes essentially data-driven, and we do not enforce any particular order of computations.
Okay, so if I try to summarize, that would be something like, usually when you work on a Bayesian model, you have to specify the graph and the order of the graph in which direction the nodes are going. In reactive message passing, it's more like kind of a non-parametric version in a way where you just like say these stuff, but you're not specifying the directions, and you're just trying to infer that through the data. How wrong is that characterization?
Not exactly like that. So indeed, the graph that we work with, they don't have any direction in them, right? So because messages, they can flow in any direction. The main difference here is that reactive message passing reacts on changes in data and updates posteriors automatically, right? So there is no a particular order in which we update posteriors. For example, if we have some variables in our model like ABC, we don't know which will be updated first and which will be the last. It basically depends on our observations. But it works like that as soon as we have new observation, the graph reacts on this observation and updates posteriors as soon as it can, without explicitly specifying this order.
And why would you do that? Why would that be useful?
So it's a very good question. So because in Bayes Lab, we essentially work with, we try to work with autonomous systems. And autonomous systems, they have to work in the field, right? So, and like in the real world environment, let's say, right? And real world environment is extremely unpredictable. If we want to be more clear, let's say we try to develop a drone which tries to navigate in an environment, and it has like several sensors, and we want to build a probabilistic model of the environment such that drones wants to act in this environment, and like in sensors it has some noise in it, like so essentially we cannot predict in what order the data will be arriving, right? Because you may have a video signal, you may have an audio signal, and these devices that record video, let's say, they also have unpredictable update rate. Usually it's maybe like 60 frames per second, but it may change, right? So instead of like fixing the algorithm and saying, okay, we wait for like new frame from a video, we wait for a new frame from an audio, then we update, then we wait again. Instead of doing that, we just simply let the system react on new changes and update posteriors as soon as possible. And then based on new posteriors, we act as soon as possible. This is kind of the main idea of reactive implementations. And in traditional software for Bayesian inference, for example, we just have a model and we have a data set, and we fit the data set to the model, and we have the posterior, and then we analyze the posterior, and it also works really great, right? But it doesn't really work in the field where you don't have time to like synchronize your data set, that you need to react as soon as you can.
Okay, I see. So that's where basically that would be this kind of reactive message passing is extremely useful when you receive data in real time that you don't really know the structure of.
Sort of, yes. Yes. We work primarily with real-time signals. Yes.
Okay, very interesting. And actually, do you have any examples? You know, any real-life examples that you've worked on, or where you know this is extremely useful to work on with RxInfer.jl, or just in general this kind of reactive message passing?
Yes. So I usually do not work with applications. So my primary focus lies in the actual Bayesian inference engine. But in our lab, there are people who work, for example, on audio signals, right? So you want, for example, maybe create a probabilistic model of environment to be able to denoise speech, or it may be like a position tracking system or a path planning system in real time. In our lab, we also very often refer to the term active inference, which basically defines a probabilistic model not only of your environment, but also of your actions, such that you can infer the most optimal course of actions. And this might be useful in control applications, also for the drone, right? So we want to infer not only the position of the drone based on sensors that we have, but also how it should act to avoid an obstacle, for example.
I see. Yeah, okay, super interesting. So basically, any case where you have really high uncertainty, right? That kind of stuff. Okay, yeah, super interesting. And so, what prompted you to create a tool for that? What inspired you to develop RxInfer.jl? And maybe also tell us how it differs from traditional Bayesian inference tools. be it in Python or in R or even in Julia, right? If I'm a Julia user, I'm used to use a probabilistic programming language in Julia. Then what's the difference with RxInfer?
Mm-hmm. Uh, this is a good question. But there are two questions in one. So about
Yeah.
inspiration. So
Yeah.
I joined the Bias Lab in like 2019 without
Mhm.
really understanding what it is going to be about. So without really understanding how difficult it is, really.
Mhm.
And the inspiration for me came from the project that I started my PhD on.
Mhm.
And basically, the main inspiration in our lab is like the so-called the free energy principle, which
Mhm.
kind of tries to explain how natural biotic systems behave, right? So, and they basically say they define so-called like Bayesian brain hypothesis and like free energy principle. So they basically say that any biotic system they defines a probabilistic model of its environment and tries to infer the most optimal course of action to survive, essentially. But all of this is based on Bayesian inference as well. So, right,
Yeah.
at the end, it's a very good idea, but at the end, it all boils down to the Bayesian inference. And basically, if you look how biotic systems work, we note that there are very specific properties of this biotic system. So they do not consume a lot of power, right? It's actually it has been proven that our brain consumes like about 20 watts of energy, right? And it's like an extremely efficient device, if we can say,
Mhm.
right? It does not even compare with supercomputers.
Mhm.
It's also scalable because we live in the very complex environment with many variables. We act in real time, right? And we are able to adapt to the environment, and we are also kind of robust to what is happening around us, right? So if something new happens, we able to adapt to it
Mhm.
instead of just failing, right?
Mhm.
And this is kind of the idea. So the inspiration for this Bayesian inference toolbox that we need to be scalable, real-time, adaptive, robust, super efficient, and also low power, right? So this is the main ideas behind RxInfer project. And here we go to the second part of the question, how does it differ? Because
Yeah.
this is exactly where we differ, right? So other
Mhm.
solutions in Python or in Julia, also very cool. There are actually a lot of cool libraries for Bayesian inference, but most of them, they have a different set of trade-off or requirements. And maybe I will be super clear. We are not trying to be better, but we are trying to be we are trying to have a different set of requirements for the Bayesian
Yeah.
inference system.
Yeah. Yeah. You're
Because
working on a different set of needs in a way.
yes, and
Yeah.
it's like application driven,
Yeah.
and
Yeah. You're trying
other
to address another type of applications.
exactly.
Yeah.
And if we directly compare to other solutions, right, they are mostly based on sampling, like HMC or
Yeah.
NUTS, or
Yeah.
maybe they're like black box methods like AGVI, automatic
Mhm.
differential variational inference, or BBVI. And
Mhm.
they're great methods, but they tend to consume a lot of computational power or like energy, right? So they do a very expensive simulation. It may run for maybe hours, maybe even days in some situations. And they were great, but you cannot really apply it in these autonomous systems where you need to, like if we're again talking about audio, it's like 44 kilohertz. So you need to really perform Bayesian inference at an extremely fast scale, and HMC or not are not really applicable in this situation.
Mhm.
So
Yeah. Fascinating. And you were talking. Well, okay, we'll get back to the computation part a bit later. Maybe
mhm.
first, I'd like to ask you, why did you do it with Julia? why did you choose Julia for RxInfer, and what advantages does it offer for your applications of Bayesian inference?
So the particular choice of Julia was actually like driven by the needs of the Bayes lab in the university, because all research which we do in the university now in our lab is done in Julia, and that decision has been made by our professor many years ago. And interestingly enough, our professor doesn't really code, so. But Julia is a really great language. So if I would choose myself, if I would still choose Julia. It's a great language. It's fast, right? So and our primary concern is efficiency. And like Python can also be fast if you like know how to use it. If you use NumPy or like some specialized libraries. But with Julia, it's really easy. It's easier. In some situations, of course, you need to know a bit more. So my background is in C and C++, and I understand like how compilers work, for example. So maybe for me it's a bit easier to write a performant Julia code. But in general, it's just really it's a nice, fast language, and it also develops fast. So in a sense that new versions of Julia they come up like every several months, and it really gets better with each release. Another thing which is actually very important for us as well is macros our macros in Julia. So for people who are listening, right? So macros are basically allow us to apply arbitrary code transformations to the existing code. And it also allows you to create like sub language within a language. And why it is particularly useful for us is that specifying probabilistic models in Bayesian inference is a bit hard or like tedious. We don't want to directly specify these huge graphs. And instead, what we did, and what Turing also did, and many other libraries in Julia, they came up with like a domain-specific language for specifying probabilistic programs, and it's extremely cool. So it's like it's much simpler to define a probabilistic program in Julia than in Python, in my opinion. And I really like this feature of Julia.
Nice. Yeah. These basically like building block aspect of the Julia language. Yeah. I've heard that.
There are other aspects I can mention of Julia. By the way, maybe I also can make an announcement regarding Julia. Is that the next JuliaCon is happening in Eindhoven, in the city where I'm currently in, and it's going to be very cool. It's going to be in PSV Stadium, in the football stadium. The technical conference about programming language is going to be on the stadium. So, so another aspect about Julia is this notorious dynamic multiple dispatch, and it was extremely useful for us in particular for reactive message passing implementation, because again, so if we think about how this reactiveness work and how do we compute these messages on the graph, in order to compute the message, we wait for inputs, and then when all inputs have arrived, we have to decide how to compute the message. And computation of the message is essentially solving an integral. But if we know types of the arguments, and if we know the type of the node, it might be that there is an analytical solution to the message. So it's not really necessary to solve a complex integral. And we do it by multiple dispatch in Julia. So multiple dispatch in Julia helps us to pick the most efficient message update rule on the graph, and it's basically built into the language. It's also possible to emulate it in Python, but in Julia it's just fast and built in, and it works super nice, in my opinion.
Yeah, super cool. Yeah, for sure. Super interesting points, and I'm very happy because it's been a long time since we've had a show with some Julia practitioners, so that's always very interesting to hear of what's going on in that field. And yeah, I would be convinced just by coming to PSV Eindhoven Stadium. Like, you don't have to tell me more. I'll be there. Let's do a live show in the stadium.
Yes, I will be there.
Yeah, that sounds like a lot of fun. And actually, so I'm myself an open source developer, so I'm very biased to ask you that question. What were some of the biggest challenges you faced when you developed RxInfer, and how did you overcome them? Because I guess that's like the main thing you do when you're an open source developer is putting out fire.
It is an amazing question. I really like it. And I even have like some of the answer in my PhD dissertation, and I will probably just quote it, but I don't remember exactly how I framed it. But I took it from the book, which is called Software Engineering for Science. So, and basically it says that people usually underestimate how difficult it is to create a software in scientific research area. And the main difficulty with that is that there are no clear guidelines to follow. It's not like designing a website with clear like a framework, rules, and you just split tasks between like people in the team. No, it's like new insights of science, like in the area where we work they happen every day, right? And the requirements for the software, they may change every day, and it's really hard to like come up with a specific design before we start developing, because the requirements change over time. Because you may created some software for research purposes, and then you found out something super cool which works better or faster or scales better, and then you realize that, well, you actually have to start over because this is just better. we just found out something cooler, and it also means that a developer must invest time into this research. So it's not only about coding, like you should understand how it all works from the scientific point of view, from a mathematical point of view. And sometimes if this is like a cutting edge research, there are no books about that, how it works, right? So we must invest time in reading papers, and also being able to write a good code, which is fast and efficient. And all of these problems, they also occurred when we developed RxInfer. Even though I'm the main author, a lot of people have helped me, right? It's like very thankful for that. And for RxInfer in particular, I also needed to learn a very big part of statistics, because when I joined the lab, I actually didn't have a lot of experience with Bayesian inference and with graphs and with message passing. So I really needed to dive into this field, and many people helped me to like understand how it all works. A lot of my colleagues, they have spent their time to explain. And even though, right, so we have already this stack of difficulties at the end, or like maybe not at the end, but the software that we use, we would like it to be easy to use, like, or user-friendly. So we already have these difficulties about, we don't know how to design it. We have to invest time into reading papers, but then at the end, we want to have a functional software that is easy to use, addresses different needs, and allows you to find new insights. So the software should be designed such that it does not impose a lot of constraints on what you can do with the software, right? Because scientific software is about finding new insights, not about like doing some predefined set of or algorithm. You want to find something new, essentially, and software should help you with that.
Yeah, for sure. It's a good point. And what do you think? What would you say are the key challenging? Sorry, the key challenges in achieving scalability and efficiency in this endeavor, and how does RxInfer address this?
So basically, we are talking in the context of Bayesian inference, and the key challenge in Bayesian inference is just that the Bayes rule doesn't scale. Right? The formula looks very simple, but in practice, then we start working with large probabilistic models. Just blind application of Bayes rule does not scale because it has exponential complexity with respect to the number of variables. And RxInfer tries to tackle this by having essentially two main components in the recipe, like maybe three, let's say three. So first of all, we use factor graphs to specify the model. So we work with factorized models. We work with message passing, and message passing essentially converts the exponential complexity of the Bayes rule to linear, but only for highly factorized models. And like highly factorized here is a really crucial component, but many models are indeed highly factorized. It means that variables do not directly depend on all other variables. They directly depend on maybe a very small subset of all variables in the model. And the third component here is variational inference. So because it allows us to trade off the computational complexity with accuracy. So if the task is too difficult or it doesn't scale, basically what variational inference gives you is that is the ability to impose a set of constraints into your problem, because it reframes the original problem as an optimization task, and we can optimize with up to a certain constraint. For example, we may say that this variable is distributed as a Gaussian distribution. It may not be true in reality, and we lose some accuracy, but at the end, it allows us to solve some equations faster. And we can impose more and more constraints if we don't have enough computational power and if we have large model, or we may relax constraints if we have enough computational power and we gain accuracy. So we have this sort of a slider which allows us to scale better. But here's the thing, right? We always can come up with such a large model with so many variables and so difficult relationships between variables where it still will not scale, and this is fine. But RxInfer tries to push this boundary for like scaling Bayesian inference to large models.
And actually, so you're using variational inference quite a lot in this endeavor, right? So actually, can you discuss the role of variational inference here in RxInfer, and maybe any innovations that you've incorporated in this area?
So the role I kind of touched upon it a little bit is that it acts as like a slider, right? In the controlling the complexity and the accuracy of your inference result. This is the main role. Of course, for some applications, this might be undesirable. For some applications, you may want to have a perfect posterior estimation. But for some applications, it's not a very big deal. We are talking about different needs for different applications here. And the innovation that RxInfer brings, I think it's like one of the few implementation as message passing, like variational inference as message passing, because it's usually implemented as like black box method that takes a function like a probabilistic model function and maybe does some automatic differentiation or some extra sampling under the hood. And message passing by itself has a very long history, but I think people mistakenly think that it's quite limited to like some product algorithm, but actually variational inference can also be implemented as message passing. And it's quite good. So it opens the applicability of the message passing algorithms, and also as we already talked a little bit about this reactive nature of the inference procedure. So it's also maybe even the first reactive variational inference engine, which is designed to work with infinite data streams. So it continuously updates these posteriors, continuously does minimization. It does not stop. And as soon as new data arrive, we basically update our posteriors. But in between this kind of data windows, we can spend more computational resources to find better approximation for the variational inference. But all other solutions, let's say, that are also variational inference, they basically require you to to wait for the data, then feed to the data, or wait for the entire data set, feed the data set, and then you have the result, then you analyze the result, and then you repeat. So RxInfer works a bit differently in that regard.
Yeah. Fascinating. And that, like, I'm guessing you have some examples of that up on the RxInfer website. Maybe we can link to that in the show notes for people who are interested to see how you would apply that in practice.
So RxInfer currently, I know that it is being used, like, for example, to teach students in Eindhoven University for fundamentals of Bayesian statistics. So it does not really require reactivity, but because it's kind of like easy to use and fast, like students can do some homework for signal processing applications. What I've already mentioned is that we work with audio signals and with control applications. I don't really have a particular example if RxInfer is being used in the field or by an industry. So it's primarily our research tool currently, but we want to extend it. So it's still a bit more difficult to use than Turing, let's say, Turing, which is also written in Julia. Because message passing is a bit maybe more difficult to use, and it is not that universal as HMC and NUTS. It still requires some approximation methods. So we still use it as a research tool currently, but we have some ideas in the lab how to expand the available set of probabilistic models we can run an inference on. And yes, indeed, on our documentation, we have quite a lot of examples where we can use. But these examples, they're, I would say, educational in most of the cases, at least in the documentation. And so we are at the stage where we have a lot of ideas how we can improve the inference, how we make it faster, such that we can actually apply it for real tasks, for real drones, for real robots, to make a real speech like denoise or something similar.
Definitely that would be super interesting. I'm guessing for people who are who are into these and also just want to check out. I've been checking out your website recently to prepare for the episode. Actually, can you now? So you've shared some the overview of the theory, how that works, what RxInfer does in that regard. Can you share what you folks are doing with lazy dynamics, how that's related to that, and how does that fit into this ecosystem, let's say?
So lazy dynamics, we created this company to commercialize the research that we do at our lab, to basically find funding to make RxInfer better and ready for industry. Because currently, let's say, RxInfer is a great research tool for our purposes, right? But industry needs some more properties to the addition that I have already mentioned, right? For example, indeed, the Bayesian inference engine must be extremely robust, right? It does not allow to fail if we really work in the field And this is not really a research question. It's more about like implementational side, right? It's like good code, good code coverage, like great documentation. And this is what we kind of also want to do with Lazy Dynamics. We want to take this next step and want to create a great product for other companies, such that they can rely on RxInfer maybe in their research or maybe even in the field, right? And maybe we create some sort of a tool set around RxInfer that will allow you to maybe debug the performance of your probabilistic program or your probabilistic inference, right? It's also not about research. It's about like having it more accessible to other people, like finding bugs or mistakes in their model specification, make it easier to use. Or maybe, for example, we could come up with some sort of a library of models, right? So you would want to build some autonomous system, and it may require a model for audio recognition. It may require a model for video recognition, and this kind of set of models, they can be predefined, very well tested, have a great performance, super robust, and basically Lazy Dynamics may provide an access to this kind of a library, right? So, and for this kind of, because this is not a research related questions, it must be done in a company with like very good programmers and very like good code coverage and documentation. But for research purposes, RxInfer is already a great toolbox, and basically many students in our lab, they already use it. But yeah, because we are all sitting in the same room, let's say on the same floor, we can kind of brainstorm, find bugs, fix it on the fly, and they keep working that. But if we want for RxInfer to be used in industry, it really needs to be a professional toolbox with like a professional support.
Yeah, I understand. That makes sense. Surprised you can I don't know when you sleep though between the postdoc, the open source project, and the company.
So yeah, it's a great comment, but yeah, it's hard.
Yeah, hopefully we'll get you some sleep in the coming month. To get back to your PhD project, because I found that very interesting. So your dissertation will be in the show notes. But something I was also curious about is that in this PhD project, you explore different trade-offs for Bayesian inference architecture, and you've mentioned that a bit earlier. But I'm really curious about that. So could you elaborate on these trade-offs and why they are significant?
Yes, we already touched a little bit about that. So the main trade-offs here are kind of computational load, efficiency, adaptivity, high power consumption, and another aspect actually which we didn't talk about yet is structural model adaptation. So this is the requirements that we are favor in RxInfer, and this is the requirements that were like central to my PhD project. And this all arises, all of these properties, they are not just coming from a vacuum, they are coming from real-time signal processing applications on autonomous systems. We don't have a lot of battery power, we don't have a very powerful CPUs on these autonomous devices, because essentially what we want to do also is that we want to be able to run a very difficult, large probabilistic models on a Raspberry Pi, let's say, right? And Raspberry Pi doesn't even have a GPU, so I mean we can like buy some small sort of a GPU and put it on a Raspberry Pi, but still like the computational capabilities are very, very limited on edge devices. And for example, one may say, okay, let's just do everything in the cloud, which is a very valid argument actually, right? But we also, in some situations, the latencies are just too big. And also maybe we don't have an access to the internet in some areas, but we still want to like create this adaptive Bayesian inference systems like a drone that they may explore some area, maybe in a mountain or something where we don't really have an internet, so we cannot really process anything in the cloud. So it must work as efficient as possible on a very, very small device that doesn't have a lot of power, doesn't have a lot of battery, and still this should work in real time. Yeah, I think this is mostly the main trades-off. And in terms of how we do it, right, we use this variational inference and we sacrifice accuracy with respect to scalability. Reactive message passing allows us to scale to a very large models because it works on factor graphs.
Yeah, and I think these are very important points to make, right? Because always when you when you work and you build an open source package, you have trade-offs to make, right? So that means, well, you have to choose whether you're going to a general package or a more specified one, and that will dictate in a way your trade-off plan. In RxInfer, it seems like you're quite specified specialists of message passing inference. So the cool thing here is that I'm guessing you can make more opinionated choices, because you're like, no, our main use case is that, and so we can use that. And the variational inference choice, for instance, is quite telling, because in your case, it seems to be really working well, whereas we could not do that in PyNC, for instance. If we remove the ability to use HMC, we would have quite a drop in the user numbers. So that's always something I try to make people aware of when they are using open source packages. Yeah, you cannot do everything.
Yeah, exactly. So I actually really, when I have a need, I really enjoy working with like HMC or NATS-based methods because they just work, just like magic. Here's the trade-off, right? They work magically in many situations, but they're slow in some sense. Let's say they're not slow, but they're slower than message passing. So, and here's this trade-off. So user-friendliness is really, really important key in this equation.
Yeah, and what do you call user-friendliness in your case?
So what I refer to user-friendliness here is that a user can specify a model, press a button with HMC, and it just runs, and a user gets a result. Yes, a user needs to wait a little bit more, but anyway, like user experience is great. Just specify a model, just run inference, just get your result. With RxInfer, it's a bit less easier because in most of the cases, message passing works like that it favors like analytical solutions on the graph. And if analytical solution for a message is not available, basically a user must specify an approximation method. It actually also can be HMC, just in case. But still, RxInfer does not really specify a default approximation method currently, though we have a research that we try to define a default approximation method. But because it does not define it currently, if a user specify a complex probabilistic model, it will probably throw an error saying that, okay, I don't know how to solve it. Please like specify what should I do here and there. And for a new user, it might be a bit unintuitive how to do that, what to specify. So for HMC, there's no need to do it, it just works. But if RxInfer, it's not that easy yet. That's what I was referring to, user friendliness.
Yeah, that makes sense. And again, here the interesting thing is that the definition of user friendliness is gonna depend on what you're trying to optimize, right? What kind of use case are you trying to optimize on?
Yes.
Actually, what What's the future for RxInfer? What are the future developments or enhancements that you are planning?
So we have already touched a little bit about like lazy dynamic side, which tries to make a really like a commercial product out of RxInfer with like great support. This is one side of the future, but we also have a research side of the project. Research side of the project includes structural model adaptation, which in my opinion is quite cool. So what it basically means in a few words is that we may be able in the future to change the structure of the model on the fly without stopping the inference procedure. And you may need it for several reasons. For example, computational power, computational budget changed, and we are no longer able to run inference on such a complex model. So we want to reduce the complexity of the model. We want to change its structure, maybe put some less demanding like factor nodes. And we want to do it on the fly without actually stopping the inference, because for like sampling based methods, if we change the model, we basically are forced to restart because we have these chains, and it's quite difficult to reuse the previous result if the structure of the model changed. But with factor graphs, it's actually possible. So another point why we would need that in the field is that if you could imagine different sensors, so we have different observations, and one sensor all of a sudden just burned out or glitched or something like that. So essentially, we are not longer having this sort of observation. So we need to change the structure of our model to account for this glitch or breakage of the sensor. And this is also where reactive message passing helps us, because because we do not enforce a particular order of updates, we stop reacting on this observation because it's no longer available. And we also change the structure of the model to account for that. Yeah. Another thing for the future of RxInfer in terms of research is that we want to be to support natively different update rates for different variables. And so what I mean by that is that if you imagine an audio like recognition system, let's say, or audio enhancement system, let's say, and you model the environment of like a person who is talking around, or like several persons, and let's say their speech signal arrives at the rate of like 44 kilohertz if we are talking about a typical microphone, but their environment, where are they currently sitting, doesn't really change that fast, because they may sit in a bar, and it will be a bar an hour later. So there's no need to infer this information that often as their speech. So it changes very rarely. So we have a different set of variables that may change at different scales. And we want also to support this natively in RxInfer, so we can also make it easier for the inference engine, so it does not spend computational resources on variables which are not updating fast. We want to be able to support non-parametric models in RxInfer, and this includes like Gaussian processes. And we have a research, so currently we have a PhD student in our lab who is working a lot on that, and he has a great progress. It's not available in the current version of RxInfer, but he has like experiments and it works all nicely. At some point it will be integrated into the public version. And yeah, and it just, just maintenance and fixing bugs and this kind of stuff, improving the documentation. So the documentation currently needs improvement, because we have quite some features and additions that we have already integrated into the framework, and we happily use them ourselves in our lab for our research, but it's like maybe poorly documented, let's say. So other people in theory can use this functionality, but because they cannot go to my table in the office in the Eindhoven University of Technology, they cannot ask how to use it properly. So we should just put it into the documentation, and so other people can use that as well.
Yeah. Yeah, yeah, that makes sense. That's a nice nice roadmap for this year. And looking ahead, what's what's your vision, let's say, for the
Hmm.
future of automated Bayesian inference in the way you do it, especially
Hmm.
in complex model like yours? Yeah, what's your vision about that? What would you like to see in the coming years? Also, what would you like to not see?
A good question. So, in my opinion, the future is very bright. The future of automated Bayesian inference, and like a lot of great people working on this and start to work on that. More people are coming, right? So many toolboxes in Python and Julia, like PyMC, Turing in Julia. In R, there are like in C++, 10. So many implementations, and it's only getting better with every year,
Hmm.
right? But I think, in my opinion, the future is that there will be several applications, like in our case, this autonomous systems, or maybe something else. And these packages, they will basically not really compete, but in a sense, they will like for different applications, you will choose a different solution, because all of them will be kind of great in their own application. But I'm not sure if there will be like a super ultra cool method that solves all problems of all applications in Bayesian inference. And maybe we'll have, who knows? But in my opinion, there will be always this trades off in different applications, and we'll use different methodologies.
Mm-hmm. Mm-hmm. Yeah. Yeah. Um, yeah, that makes sense in a way. I like your point here about all these different methods cooperating in a way because they are addressing different workflows or different use cases.
Hmm.
Right. So
Yeah.
yeah. Definitely, I think
I,
we'll have stuff to
yeah,
learn from one type of application to the other.
exactly. I like this analogy of we don't cut a bread with a fork, but it doesn't really make a fork a useless tool. I mean, we,
Mm-hmm.
we can use a fork for something else, and
Yeah.
and we are not eating a soup with a knife, but it doesn't make a knife a useless tool. So these are tools, they are great, but for their own purposes.
Yeah.
So
Yeah.
RxInfer is like a good tool for like real-time signal process application, and Turing in Julia is like a great tool for other applications. So
Yeah.
we'll just live together and learn from each other.
Mm-hmm. Yeah. Fascinating. I really love that. And well, before closing up the show, because don't want to take too much time of you, but
Hmm.
do you have any a question I really like asking from time to time is if you have any favorite type of model that you always like to use and you want to share with listeners?
You mean probabilistic model?
Sure, or it
Uh,
can be a different model for sure. Yeah, but yeah, in general,
um,
probabilistic model.
I actually, yeah, I mentioned a little bit that I do not really work from application point of view. I really work on the compiler for Bayesian inference. So I don't really have a favorite model, let's say. It's hard to say.
Yeah, that's interesting because basically you work. That's always an interesting position to me because you really work on the like basically making the modeling possible, but usually you're not one of the people using that modeling platform yourself.
Exactly,
Yeah,
yes.
yeah. That's always something really fascinating to me because me, I'm kind of on the bridge, but a bit more to the applied modeling side of things. So I'm really happy that there are people like you who make my life easier and even possible. So thank you so much.
Yeah, that's cool. That's cool.
um, awesome, Dmitry. That was super cool. Thanks a lot. Before letting you go, though, as usual, I'm gonna ask
Hmm.
you the last two questions. I ask every guest at the end of the show. First one: if you had unlimited time and resources, which problem would you try to solve?
Uh, yes, I thought about this question. It's kind of an interesting one. Um, and I thought like it would be cool to have, if we have us infinite amount of time, to try to solve some sort of unsolvable paradox, right? Because we already have unlimited time. So, and one of the area which I never worked with, but I'm really fascinated about is astronomy. And one of the paradoxes in astronomy, which is kind of I find interesting, but maybe it's not really a paradox, but anyway, is like Fermi paradox, which basically, in a few words, it tries to explain the discrepancy between the lack of evidence of other civilizations, even though apparently there is a high likelihood for its existence, right? So this is maybe a problem I would work on if I would have an infinite amount of resources. I can just fly into space and try to find them.
That sounds like a fun endeavor. Yeah, for sure. I'd love the answer to that paradox for sure. And people are interested in the physics side of things. There is a whole bunch of physics related episodes of this show. So for sure, refer to that. I'll put them in the show notes. My whole playlist about physics episodes.
Yeah, I know. Cool.
And I know also you're a big fan of Aubrey Clayton's book, The Bernoulli's Fallacy. So I also put this episode with Aubrey Clayton in the show notes for people who have missed it. If you have missed it, I really recommend it. That was a
I know this episode.
Yeah. Awesome. Well, thanks for listening to the show, Dmitry. Awesome. Well, thanks a lot, Dmitry. That was really a treat to have you on. I'm really happy because I had so many questions, but you helped me navigate that. I learned a lot, and I'm sure listener did too. So as usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Dmitry, for taking the time and being on this show.
Yeah, thanks for inviting me. It was a pleasure to talk to you. Like really super nice and super cool questions. I really liked it.
Let me show you how to be a good breezy and change your predictions after